So the Pai Lin Travel Award is a really wonderful thing that we have every year. It is funded by the widow of Pai Lin Lee, who for many years was the institution's representative in Canada. And we're really grateful to Anita Lee for her wonderful generosity in funding this award. And the award is for between £1,000 and £3,000 that goes to somebody who is planning to study for 4 to 6 weeks outside their home country on a topic related to construction materials. And we have really interesting back catalogue, of award winners and work that they have done. It's quite an intensive period, and a whole load of new connections are made and ideas uncovered, and it's really great. So this year we have 2 award winners from the 2017 award. The 2018 is going to be awarded soon. And I'm pleased to just let you know who they are, and then we're going to hear from them, and we'll have some questions. I would say that because we're recording, please do speak clearly as a speaker. Unless you've been wired up otherwise, speak into this lectern rather than wander around. And for people asking questions, I'll repeat your questions so that they are clear to people who are listening online or later. So our first speaker will be Charlotte Murphy, who travelled to the States to study accelerated bridge construction. And Charlotte is a graduate from Cambridge who works at Arup. And our second speaker is James Lomas, who is a graduate from Leeds and works at WSP. And he'll be talking about designing bridges for manufacture and assembly. So these are... residential properties, I beg your pardon, just repeated that, didn't I? So James is going to talk about new approaches to the construction of residential properties, and he went to Japan, the Netherlands and Malaysia, where there are some amazing things happening, and have been for many years actually. I lived in Japan for a while, and their approach to modular housing in the 90s was ahead of a lot of what we do. So thank you very much to the 2 people who prepared their talks and all the work that you put in that led up to this. We're going to be treated to really interesting presentations. We will run both of them and then have Q&A afterwards. But I just would like the audience and the speakers to be very relaxed and enjoy this evening. It's going to be great. So I'm not sure if I got that order right either. Is James speaking first? Or Charlotte? James is. James. So James, please come up, and I shall move you on. Residential construction. Thank you.
Thanks a lot. Hello everyone, thank you very much for coming along today. My name's James Lomas, and I'll be taking you through my Pai Lin live topic, which is entitled Designing for Change, a New Approach to Residential Construction. I want to quickly take this opportunity to thank the institution for funding this award, and I'd definitely encourage anyone else thinking about doing it to apply. It's really a great opportunity. I'd like to start off by talking about residential construction in England. England has one of the oldest housing stocks in Europe. Nearly 1 in 5 buildings is over 100 years old. The demolition rate has halved over the last 10 years to just 0.05% of the current housing stock. The average years elapsed before a house is demolished is only 77 years, and it's estimated that 41% of all residences have undergone at least some kind of refurbishment over their lifetime, major refurbishment over their lifetime, with this number increasing to 72% for pre-1919 housing stock. So what does this tell us? With housing in such short supply, there is a great reluctance to demolish houses in England, and instead a desire to refurbish them and maintain them well beyond their intended design life. However, nearly 91%, well, 91% of all housing stock in England is made up of either masonry or masonry cavity wall construction, which is an inherently inflexible form of construction. Load-bearing walls break up the internal layouts of buildings and also prevent facade change. Also, masonry to masonry connections are wet cementitious joints, which are very difficult to dismantle in a non-destructive way. So what does this tell us? Despite the rising need in England for housing that is able to adapt to the changing needs of the user, nearly all of it is inherently inflexible. When I looked into this further, I found that a number of countries had launched often nationwide initiatives to try and incorporate flexibility and adaptability into their housing stocks. For my Pai Lin award, I decided to travel to these countries and investigate the range of initiatives that have been trialled, along with the cultural, social and economic drivers that had influenced them. The three countries I visited were the Netherlands, where I investigated the Industrial Flexible Demountable, or IFD Construction Initiative. I also visited Japan to investigate various adaptable housing schemes dating back to the 1970s. And I also visited Malaysia, who's embarking on their own program of industrialised building systems. And as part of that, they are trialling new concepts dealing with open system building. So starting with the Netherlands. So the Industrial Flexible Demountable Construction Initiative was established in 1999 by the Dutch government. It involved 69 projects, 34 of which were residential, and the program lasted for 7 years through to 2006. The program was introduced to promote flexibility, quality and sustainability in the Netherlands housing industry. IFD buildings can be described as a construction method for creating flexible housing in which the user is free to choose the size of the dwelling in question, together with details of the layout, built-in facilities and furnishing. So what do we mean by industrial, flexible and demountable housing? Industrial refers to prefabricated components that are then assembled on site. Flexible refers to the ability of a building to adapt to the changing wishes of the user. And demountable refers to the ability of building components to be removed and replaced without damaging other parts of the building. In essence, IFD buildings are essentially made up of standardized prefabricated components that can be replaced and changed over time to fit changing needs of the user. So now I do want to take you through a few example projects. So this particular project was called FlexLine project and was built in Hengelo. It involved the construction of 18 modular homes. Each home was comprised of 4 modules and up to 2 houses could be completed a day. The scheme intended to allow users to customize the size, finish and facades of their modules before they were then installed on site. The project was stopped after only 18 of their houses were completed, opposed to 50, due to spiralling construction costs. I think those 18 houses actually cost 3.1 million euros in the end, so it's pretty pricey. The IFD Today trial module was a module I actually visited during my trip to the Netherlands. It involved a modular cladding system that again could be changed over the lifetime of the structure, and also contained a modular hollow floor system which facilitated the easy change of surfaces. This was initially started as an investigation for a wider hotel company, but it ended up being just a trial module and wasn't utilised in any wider scheme. Next, I'd like to talk about the Smart House initiative. This involves 3 homes built in Rotterdam and comprised a standardised 3 by 3 metre steel framed grid with dry joints. This allowed the initial user to change the massing of their home to suit their needs at the beginning, and also facilitated easy extensions over time. The status this was turned into a catalogue product, but without any known further projects. Second from last, the Het Master project, which was completed in Verendale. Hopefully I pronounced it right. and it comprised over 20 homes. The scheme intends to allow the initial owner to change the room layout and finishes before construction was completed. Several trial homes were also allowed or built in with facilities to be able to extend over time. This project was completed and is still in use. Finally, I want to touch on another system I investigated while I was in the Netherlands, which is the De Groove Root Shoot IFD building system for semi-permanent buildings. Structures are intended to last for 15 years before all the structural elements can be demounted, taken back, refurbished, and then used again on a different project. These elements included precast slabs, precast foundations, steel columns, and timber facade panels. The maximum height of the structures was up to 4 stories, and it is still running in the country. It's important to remember that when I visited the Netherlands, it was actually over 12 years since the completion of the IFD scheme. So what was its legacy? As we've just seen with a few of the projects, many projects failed to progress past their prototype stage and failed to prove there was actually a market for adaptable housing. These IFD principles were broadly abandoned by the industry, except in the use of semi-permanent buildings where there was a clear financial incentive to use them. Despite this, industrialisation has continued to increase in the Netherlands, with over 20% of housing now using some kind of prefabricated wood or concrete construction. This is compared to 9% in Germany and just 5% here in the UK. With this has become a certain level of choice as well for the initial user, and this particular screenshot comes from a website that allows purchasers to change the dimensions of their prefabricated homes along with the addition of various features. When I looked into why the IFD principles had not been more widely incorporated in the Netherlands construction industry, I hit upon 2 probably key points. One was that there was not enough proof that the incorporation of these features would A, increase the value of your home, or B, actually be used over the lifespan of the structure if they were introduced. In short, there wasn't enough trials proving that these flexible features were worthwhile. This is partly due to the range of different features, where you can have very expensive features to make a building adaptable, including oversized foundations and oversized columns, and then very cost-effective features, including raised floor systems and hung ceilings. Another feature I found was actually that the end user, or the person most likely to benefit from these schemes, often had limited influence on the actual design and construction process. So what were my findings? The IFD project only partially succeeded in incorporating IFD principles into the Netherlands construction industry. Standardized 2D and 3D components were used to promote standardized choice for users and allow them to alter and change their buildings over time. The IFD program helped the continued push toward industrialization in the Netherlands. Post-funding, unincentivized building sector chose to only retain IFD features which clearly generated profit, i.e. greater off-site production and greater flexibility for the initial user. Design for disassembly has been broadly abandoned in the industry, except for in the use of semi-permanent buildings where there's clear financial incentive to use them. And finally, key stakeholders who adaptable features would most likely benefit often have a limited influence on the design process. And also, finally, the program failed to convince the industry there was a market for adaptable housing. Now changing over to Japan. Traditional Japanese construction has historically embodied flexible design. A traditional Japanese house is a timber frame with a repeating grid of timber columns with standardized infill components that can be moved and changed to fit the changing needs of the user. This traditional kind of timber reduced following the Second World War and the widespread fires caused by Allied bombing and the subsequent destruction necessitated a shift towards mass-produced, low-quality housing. This began Japan's unhealthy relationship with structures and a scrap and build culture where the average house in Japan is demolished after just 30 years in use, and the reuse of housing makes up just 15% of the Japanese housing market. For this reason, the Japanese government has initiated a series of flexible housing schemes since the 1970s to try and change Japan's unhealthy relationship with housing, encouraging them to maintain it and reuse it, opposed to just demolishing and rebuilding. The 4 schemes I want to quickly touch on tonight are the Kodan Experimental Housing Program, the Century Housing System, the Next 21 project, and finally the Act for Promotion of Long Life Quality Housing, which came into law in 2009. So starting with the KEP program. It was a private venture initiated by the Japanese Housing Corporation in 1973. It considered a series of movable partitions and storage systems that allow users to change the spatial layouts of their apartment over time. Studies have shown that the incorporation of these features were broadly successful, with those people with those apartments who use them far more likely to change the layout of their apartments than those people who did not possess them. Over a 32-year period, that was 54% of those people who possess these kind of movable partitions changed the layout of their apartments, compared to just 8% of those people who didn't use them. Despite this, some residents complained about rusty or faulty joints and complained that the poor sound insulation caused by the KEP walls wasn't worth the ability to change a wall once every 10 years. This then progressed onto the Century Housing System, which was started in 1988 by the Ministry of Construction after over 7 years of research. It comprised a 5-volume certification guidebook and accreditation process, of which it attempted to break down a building into 5 different types of components, depending on their service lifespan. The idea was that those components with shorter lifespans could be removed and replaced without damaging those longer life components. There was generally pretty poor uptake in the system, with only 40 known projects completed over 16 years. The 5 levels of components were deemed too complicated, both for occupants and for the contractors trying to build them. This confusion was compounded by non-technical guidance, which was initially intended to allow flexibility for contractors. And there was also considered to be insufficient financial incentives, with the purchase of new properties being given a tax exemption of approximately £7,000 or equivalent in Japanese currency at that time. Moving swiftly on to the Next 21 project, which was a trial project completed by the Osaka Gas Company in 1993 to investigate multi-unit sustainable housing. This is based on a simplified skeleton infill principle opposed to the 5 levels of components we saw before. The idea is that the concrete frame would make up the skeleton, and the infill components, including the cladding and the fit-out, could be easily removed and replaced without damaging the overall structure. The building was 5 stories high and contained 18 apartments. Features of the project include a modular facade panel which could be moved in and outwards to create balconies. This has been done several times over the scheme's 25-year program. Only 2 communal risers service the entire building, which are accessible on every floor from a communal corridor, which allows easy replacement of services over time. The concrete frame is designed to last for a 100-year lifespan, and that includes both durability and earthquake design. The floors have been designed for a high imposed load to allow to accommodate changes of use, and a generous 3.6 floor-to-floor height has been incorporated, which allows a 240 mm raised floor zone, which again helps to facilitate the change of services. So that brings us on to the Long Life Quality Housing Act of 2009. This act intended to learn from all the mistakes of the previous projects. It decided to use a skeleton infill principle similar to the Next 21 project, which was so successful. It offered generous tax incentives to buyers, an equivalent of a £40,000 tax exemption if you bought a new house, compared to the far less generous Century Housing System. And again, learning from the Century Housing System, it included more technical guidance, including that the frame should be designed should last for 200 years with only basic maintenance. Minimum spatial requirements for apartments, including a minimum floor-to-ceiling height of 2.65 metres. Rise would be positioned and sized to facilitate the change and replacement of services. And finally, every building complying with the Act will have to have a maintenance plan for structural, waterproofing and drainage systems. I should add that this is only very much a snapshot. The guidance goes into a lot more technical detail. The scheme was a massive success, with over 808,000 long-life quality houses built up until March 2017. The only exception to this was in apartments. This was the 747 residence I visited near Abina, and I got to meet the architect, and when I asked them why weren't they complying with the Act, they complained that the rise requirements were still too stringent. So the Act isn't quite there yet, but the uptake has been quite incredible from the industry. So what were my findings from Japan? So Japan has experimented with flexible housing for the last 50 years as a way to tackle democratic changes and poor average housing lifespans with mixed success. Best practices have emerged over time, and overbearing policies such as movable internal fit-outs have been left behind. Simplified technical guidance has been established as the best way to motivate the industry, and these ones were based on the Next 21 housing project. Because of the relatively new nature of this program, time is still required to tell whether these features will perform as they intended over time. I now very briefly want to touch on Malaysia, where I went to investigate the Industrialised building system project there. The Malaysian government has championed it since 1960 as a way of modernising the construction industry and to increase Malaysia's dependence on foreign unskilled labour. The vast majority of this construction comprises the assembly of precast components that have been prefabricated off-site. The uptake has been very impressive from the Malaysian construction industry, with 72% of private sector projects now designated industrialised building system projects in 2016. The reason I went over there was to investigate the concept of open system building, where they attempt to standardise components across the industry. As we saw with the Netherlands project, the idea of using standardised components to offer change and flexibility, I basically went to establish whether this was also being done in Malaysia. I was sorely disappointed. I visited this was a typical IBS project I visited near Kuala Lumpur. The project involved low-bearing precast walls, which obviously breaks up apartment layouts and prevents changes. All ducting and electrical cables, as you can see in the second picture, were actually cast into the wall, which prevents any changes in services. The precast walls were painted on both sides, with one side forming the outer facade and the other one forming the internal layout, which again prevents changes to facade over time. And finally, all precast panel floors were laid with a structural screed, which completely eliminates the option of being able to dismantle these structures in a non-destructive way. So very briefly on Malaysia, I discovered that the introduction of industrialised modular construction had not resulted in any kind of adaptable housing, and a culture for wet chemical joints had hammered any benefits which could have been offered by open system building. So what were my overall conclusions? Designing for change costs money. The construction sectors in all three countries have resisted its incorporation. Key stakeholders who would most benefit from adaptable features often kept away from the design and construction process. There is currently not enough evidence to prove that providing adaptable features would either increase property value or would be sufficiently utilised over their lifetime if they were incorporated. So I believe that further research is really required to prove the benefit of adaptable housing. Finally, it is possible to introduce adaptable features into housing stock using government policy. However, this must be properly targeted and properly incentivised. So what lessons can we learn from the UK? As prefabrication grows in the UK, we should make the effort to create customisable, flexible, high-quality homes and definitely try and steer clear from the kind of modularisation we saw in Malaysia. Finally, modest changes could easily be introduced to UK building standards, for instance BREEAM, to mimic what was done with the Japanese Long Life Housing Act to kind of make the England housing stock more flexible. That's all. Thank you very much for listening.
Hello everyone, thank you for coming. My name is Charlotte and I work as a bridge engineer at Arup. The Pai Lin Travel Award has funded this research into techniques for joining precast concrete components together. As the map shows, the stars show everywhere I went, my research was focused on the USA, and the reason for this is the Federal Highways Administration has invested heavily in this field. This slide outlines what I'm going to cover in my talk. Motivation. Why is this topic important? Secondly, accelerated bridge construction. What have they been doing in the USA? Moving then on to enabling technologies. What has emerged from the accelerated bridge construction scheme and how can we use them? And then I'm going to talk through a case study where I will demonstrate how the enabling technologies have really improved the construction of bridges in the USA. And then I will conclude. So, why is improving the joints between precast components important? It is undisputed, as we've also heard from the talk before, that off-site manufacture brings benefits to construction. Safety, quality, faster construction, I could go on. However, the key issue with the off-site manufacture of concrete is that it's very difficult to join the precast concrete components together. As part of my master's thesis, I investigated off-site manufacture efforts in the UK with respect to bridge components. One of the key findings was that the lack of joining technologies available in the UK was pushing development towards permanent formwork solutions. In the UK, we use mechanical reinforcement couplers or conventional in-situ stitches. Both of these have their downsides. Mechanical reinforcement couplers demand tight tolerances, and in-situ stitches take up quite a lot of space. For example, research by Tony G showed that it was not feasible to precast more than 60% of a bridge deck due to the reinforcement lap lengths that are required between the components. These two diagrams are examples of precast abutment solutions that have been developed by Lang O'Rourke and have been implemented. Both of them use the precast concrete as a permanent formwork. The reinforcement cages within them are assembled conventionally, and then the inside is filled with in-situ concrete. This solves the joining problems, as the reinforcement continuity between the abutment and the foundation is provided within the in-situ section, and it does lead to rapid construction. However, it's not a particularly material efficient solution, as once the in-situ concrete is cast, the precast concrete formwork is redundant. This is really important because in December of 2017, the UK government announced that projects utilising off-site manufacture will be favoured in tenders from 2019. So more off-site manufacture is coming to our industry. And this research aims to ensure that the industry embraces off-site manufacture in the best way and also in a sustainable way. Accelerated bridge construction. Why have I chosen the USA? The USA has major problems to address with its infrastructure, As this slide highlights, 9.1% of bridges in the USA were classed as structurally deficient in 2015, and it's an issue that affects the whole country. The reason I have researched the developments in the USA is due to the way that the Federal Highways Administration, similar to our Highways England, has been approaching this. It's been very proactive. The Federal Highways Administration has set up the Accelerated Bridge Construction Initiative to help rebuild its infrastructure in a way that won't bring the country to a standstill. This comprises of the University Transportation Centre, which is a group of universities that pool their research, and the Federal Highways Administration also has its own research centre, the Turner Fairbanks Centre. On top of the investment that the Federal Highways Administration is putting into these research task forces, it also provides additional funding to the State Department of Transports to build bridges using the accelerated bridge construction techniques. So it is not only driving research, but it is also incentivizing implementation. Accelerated bridge construction is very, very broad, and it covers everything from project management techniques to new construction materials. It is defined as anything that will speed up bridge construction. The recent bridge collapse in Florida was using accelerated bridge construction techniques. This bridge was partially built nearby and then rolled into position. Using these techniques meant that the road closure was only needed for 6 hours, and it would have been much longer if they had not used accelerated bridge construction techniques. However, we're all aware of the tragic events that occurred next, and we're still waiting to hear what the actual cause of that disaster was. But before and after Florida, there have been many successful accelerated bridge construction projects, over 200 now, and these have all been reducing the impact of infrastructure upgrades on the US public. My research sits within the construction materials and methods side of accelerated bridge construction. So I focus my research on two enabling technologies that have come out of the Accelerated Bridge Construction Scheme: grouted splice couplers and ultra-high performance concrete field cast connections. So I'm now going to talk to you about these in a bit of detail. So grouted splice couplers are a more construction-friendly version of mechanical reinforcement couplers. Instead of having a mechanical connection between the two reinforcing bars, force is transferred from one bar to the other through a high-strength grout. One precast component on the left is cast with a grout sleeve inside it attached to a reinforcing bar. The sleeve is filled with grout, and then a reinforcing bar from the second component is inserted inside. Once the grout is set, you then have reinforcement continuity between the two components. Grouted splice couplers can be gravity fed, such as if you look at the far left, where the splice sleeves in the bottom, fill them up with grout, and then insert your components. But they can also be pump fed using the inlets that you can see there. And that means that they're very versatile, that you can have your components in any orientation and you're still able to make the connection. They're also relatively compact. They can be used when the reinforcement spacing is at 150 millimeters. So they don't limit or change the designs that we would make normally. And they're actually very standard pieces of kit in America now in the non-seismic regions. And they allow sort of almost Lego-like connection of connecting components together. So the second technology that I'm going to talk about is ultra-high performance concrete. Ultra-high performance concrete is a low water-to-cement ratio mix of concrete, and it's reinforced with discontinuous high-strength fibers. You can see a picture of them up in the corner. UHPC has a compressive strength of over 160 megapascals and a tensile strength of 8 megapascals. It fails in a ductile manner, as you can see, unreinforced, it fails in a ductile manner. And it also has a discontinuous pore structure, meaning that it's practically impermeable and therefore very durable. Research commissioned by the Federal Highways Administration has developed guidelines for using the UHPC in reinforcement splice joints. This allows and what they do is they develop guidance, which means that this technology can be deployed very rapidly into bridge projects, and they don't have to wait for it to be incorporated into codes. if the State Department of Transport approves the use of the Federal Highways Administration guidance, the joints can be used. And this is spreading across lots of different states in the US. Due to its high strength, a 25 millimeter diameter reinforcement bar only requires 200 millimeters of embedment length, which is about a fifth of what we'd expect in the UK using normal strength concrete. And this short embedment length allows joints to be relatively compact. So we can see in the picture here, this is a precast deck slab. The joints are minimal. We would not see that in England. So now I'm going to move on to my case study to show you what these joints, what these joining techniques, the grouted splice couplers and the ultra high performance concrete allow us to achieve. So there are 6 bridges, you can see here labelled 1 to 6. They're all along Interstate 78, which is the main trunk route across Pennsylvania, and it leads to New York City. There's a big problem with the existing bridges on this route is that they don't have enough underclearance and frequently get hit by trucks, so they are needing to upgrade and replace a lot of them. The aerial photo shows the location, and the picture here shows what the bridges, what a typical bridge that's going to be replaced looks like. Each bridge that you can see here was replaced in 40 days. To give a comparison, bridges A and B down to the west were also replaced within the last 5 years using conventional methods, and the replacement of each of these bridges took 12 months. So we've got a 90% reduction in site time using accelerated bridge construction techniques. One other really interesting thing about this project is that all of the 6 bridges replaced using accelerated bridge construction techniques were all within the same contract. So they had the same client, they had the same designers, same site team. And that meant that lessons learned from one bridge were carried forward to the next bridge. And this level of repeatability isn't often seen in engineering. So that was another interesting part of this project. This is an image of one of the finished bridges. The new bridges all have a single span of approximately 36 meters and are simply supported. They've got precast, pre-stressed beams and a composite full-depth precast deck. All of the bridges had similar final appearance and architectural languages, but they were all different. They had different spans, different skews, different widths, different foundation types. No 2 bridges were exactly the same. However, each bridge was manufactured using the same methodology. The set of parts for each bridge was different in geometry, but the assembly method and the joints used was the same. And this diagram shows an example of the precast supplier's 3D assembly model for the bridge. It shows the precast footings. These are joined to each other using a shear key. The precast abutment components. These are joined to the footings using grouted splice couplers and joined to each other using a shear key. And the precast deck panels and approach slabs are joined to each other using ultra-high performance field cast connections. And as you can see from the chart here, these bridges were 86% precast concrete, and this would not be possible in the UK. The value we see here is so high due to the efficient joints between the precast components. Next, I'm going to show you a video of the construction, but first I'm going to orientate you so when you watch the video, you sort of know what you're looking at. The interstate is running east-west across the picture, and the bridge that's going to be replaced is running north-south. There was a site office up the top, and this bridge site was lucky. It had 2 temporary storage facilities for the precast relatively close by. And the camera location is just here. So when we were watching the video, that's what you're looking at. So bridge construction in 40 days. So this is the original bridge. We're going to see it be dismantled. There we go. Original bridge is gone. And now they're starting to do the earthworks for the new foundations of the new bridge. And then the next construction activity they'll do is they'll cast a blinding slab. So blinding slab going in, and then this is when it starts to get rapid. So we're about to put the foundations in. Done. Hope you didn't miss that. And then today, here come the abutments. And then what they're doing, so they're propped until the grout is set, and then props are removed, waterproof to the back, and then we can start backfilling to be able to build the next bit. They've put in like bearing slabs for the beams. This allows extra tolerance and gives them that sort of last minute moment to be able to make sure the level's right. So that's a sort of design feature that's built in. Oh, in come the beams, very quick. And then we've got the deck slabs coming in this evening. I'm there in that video somewhere. Yeah, so that's deck slabs in. The diaphragms at the end of the bridge are done in situ. The geometry there is very complicated, and they've not yet found an efficient way to do that using precast. So what we're going to see next is they're going to start filling up the deck with the UHPC, and also start preparing the bridge for the approach slabs that are coming in. So yeah, that's the deck finished. They've put all of the UHPC in, approach slabs in, done. It's so quick when it happens in the video. And then now, this is something they do in the US. They often put a concrete overlay over the bridge, which takes ages to cure. So if you see, this is like 25% of the program is this like 5 mil overlay that they put on. But once that's cured, they come along, they can paint the road lines on, and then the bridge is open. So having seen that construction, the bits where the precast components actually come in are so rapid, and those are the bits on site that often will take weeks. So it was impressive to watch. So just to summarize what we've just seen, that was a 36-meter interstate overbridge going in 40 days, and removing of the existing one. Each bridge comprised of 124 precast components, and there were no issues on any of the bridges of the components not fitting together. I'm just going to sort of step through in a bit more detail these pictures because it's quite quick in the video. So here we have the foundation slabs going in. You can see them being lifted in. There we have the cutouts for the shear keys and all of the protruding reinforcement for the grouted splice couplers. Here we have our abutment piece coming in, and again you can see the protruding reinforcement, and then someone will follow the installation of these pieces with the grout hose, grouting up every single coupler. And there are a lot of couplers, but it actually doesn't take that long once you've got the pump running. So the grouting of the couplers, even though there's a lot of them, isn't like a bottleneck in the construction procedure. Deck panels being lifted in. This, I think, due to the precast nature and the repeatability nature, they planned to do the deck lifting in 2 nights, and we saw it going in 2 nights over the video. But on the first night, they were expecting it to take 10 hours to put all of the deck slab pieces in, but it actually only took 4 hours. So, and because the pieces weren't at the site, everyone got to go home super early because they couldn't do it that day. And that was sort of a running theme with this construction, that things were completed way ahead of schedule because everyone was so ready and knew exactly what they were doing, because although the bridge is a different shape, every single activity they were doing was the same as they'd done before. So that sort of shows the benefits of manufacturing bridges as opposed to constructing bridges. And here we've got a close-up of what these precast deck panels look like. And one thing I'd like to say about the deck panels, which I think the Federal Highways Administration research has really a big benefit of it, is that it gives design guidance. It doesn't give standard details. So if you were in the US and you wanted to design a bridge using UHPC connections, there's not one way to do it. There's any way to do it within the rules in the guidance. And that means that you can develop joints that really suit your project. And I think that's why it's been so widely deployed across the US, because people aren't limited to sort of standard connections. Each bridge can be done in its own way. And these bridges show that the construction industry can move to be more of a manufacturing process. And what I've shown you here is now considered to be quite standard construction within the USA. I went to a conference in Miami where lots of different people were presenting projects they'd worked on, and this is normal. Like, it was no longer a flagship project. and it's happening across the US. And one other thing is that people in the UK are often not fully committed to precast construction over concerns of tolerance, cost, general unknowns. But I think these 6 bridges and many other projects in the US show that these risks can be managed and precast construction can be a success. So finally, to conclude, I really believe this project and this research shows that governments should be investing and developing new technology. Things have moved so fast in the USA because the drive for change has come from the Federal Highways Administration. Too often in the UK, asset owners hope for innovation when projects have tight time and tight budget. Too often, the owners do not want to deviate from what is currently in the standards, and this will not allow our industry to improve. I do not think we should copy exactly what the Americans have done. I think some of their solutions do require further development and have perhaps been deployed too fast on live assets. But that doesn't mean that we shouldn't do our own research here. And so next steps for my research, I hope that through this talk and also the follow-up article in the iStruct, engineers in the UK will start to realise what's happening in the US and that things can be built much faster than what we're doing now. And I'd also like to try and push this research out into client organisations to show that the benefits in the US have really come from the fact that the clients are investing and these technologies aren't popping up on individual projects. So we should learn from the USA. They have changed the baseline of bridge construction, and we should learn from the Federal Highways Administration's approach to innovation as it delivers. Thank you very much.